to our third meetup this autumn. Thank you for all coming. So we have today a very interesting topic and like two honorable guests that came here from Switzerland today. So first one is Edward Thompson here, and second one is Alistair Stewart. We will have two talks. So Edward will talk about Polkadot, maybe in general, and Alistair will be later on talking about consensus mechanisms. So we have a very interesting talk to look forward to. And maybe I will just mention that you guys feel free also during the session to eat some cookies and cakes we have there in the back end. And I'll also mention that our next meetup in December will be with Neufund, who will come on 5th of December, so stay tuned for that for sure. And maybe without further ado, Edward, the floor is yours now.
Thanks. So, let's kick this one off. It's my second time in Bratislava, first time presenting on Polkadot. I'm from the Web3 Foundation, along with Alistair. We're normally based in Zug, so Crypto Valley in Switzerland. It's a very nice place. We are the Web3 Foundation, we are a Swiss foundation, and we are funding the development of Polkadot. So this is a graphic that we have on our website. It isn't meant to be our logo, but it kind of became our logo. This was just meant to be a really cool graphic, and then actually became our logo. So if you're wondering what it is, it's just a cool graphic, and unofficially our logo. So this is me. You can catch me on Twitter. I'll try to behave. I can't promise. If you're easily offended, probably don't follow me, although I would say I'm quite well behaved now. And then my email address. I'm generally happy to take any questions, and I know you're going to forget about this, so I have a slide with this later on. So you'll probably think, I don't have any questions now, but then when we get to the end, you're like, shit, I should have asked him some questions. And I also just swore live on stream. Apologies to everyone at home. So, a little bit more of the Web3 Foundation. We're not the Polkadot Foundation, but we are really excited about Polkadot for obvious reasons. But we have this grander, broader vision of Web3. So Web3 is an idea of a decentralized internet, and in our view of the world, we think there's going to be a lot of blockchains in there. So we have a very blockchain-heavy view of Web3. Not everyone agrees, but we think it's a sensible one, and it's the one we're sticking to. So that's a little bit about who we are. Gavin Wood, he is the president of our foundation. You probably know him. He is a co-founder of Ethereum and did a lot of the coding for Ethereum back in the early days. We're also hiring. We have some, I think all of these positions are still open. If you forget Alistair, please shout out and correct me. I may have made a mistake, but I think they're open. Social media manager, so someone to look after Telegram and Reddit and all of our social channels, and ideally they would also be based in Zug. We have possibly still a decentralized algorithms researcher, but maybe we don't now. Alistair's giving me a funny look, so we might have filled that one. Ideally also based in Zug, but maybe remote could also work, and then something around community and events. So take a note of the link if you're interested, otherwise email me afterwards. I will have my email address again at the end. And now to start talking about Polkadot itself, which you really came for. I felt like I had to talk about the Web3 Foundation. Most people don't know who we are. Most people tend to think we're parity. We're obviously not parity. We have different offices, different people, and essentially geographically different. So, worth noting. This is the overview of what I want to talk about. Essentially, I will say what is Polkadot, give you some historical context of kind of where we're going, and then present, I think it's 7 problems of what we have on blockchain right now. And then we're going to present Polkadot's, or I'm going to present Polkadot's solution to each of these. And I'm going to try to convince you as best as I can that they are real problems. You probably know about them already, like scaling, and then I'm going to try to convince you that the solution that we have is workable or good enough. So I don't expect you to read this. Text slides are very boring, so let's move on. Who's involved? Web3 Foundation, so that's us, yay, we're funding it. And we have Parity, which is the logo on the right-hand side, and they're doing the first implementation. So Polkadot is not owned by us, it's not owned by Parity, it's a protocol, and we are very much about decentralization, so we are paying for the protocol to be designed and built, and we're also very interested in getting another team to build another implementation of Polkadot in a different language. So right now, Parity are building it in Rust, and we also want to get people to build it in Go or C++. So that's something we are going to fund. So it's not going to be just about Parity, even though a lot of people think that that's just the case, but it won't be. So that's a bit about who we are, who's involved. And now to give you what is Polkadot in a single sentence. So, this is what Polkadot is in a single sentence. It's a little bit abstruse, and you may not know what it means right now, but hopefully by the end of the presentation, this will make a lot of sense. So what is it? A heterogeneous multi-chain technology. So what that is we're saying that you can have many different blockchains connected together. So many blockchains, multi-chain, and heterogeneous means that each of the chains can be different. They don't have to be the same. So if you take something like Ethereum, that can be one type of chain. You can take something like Zcash, that's another type of chain. Something which has a different state machine, that's the heterogeneous part, and we're saying that within our platform of Polkadot, you can have each of these, or a blockchain which looks like each of these, working together. So that's what we're going to try and work towards. So this is kind of blockchain 101. The developers in the room probably groaning, I know you've heard all this before. People who are maybe not developers or maybe not so sure of the history, let me try to breeze through this as quickly as I can. Does everyone know like Bitcoin 101 or blockchain 101, like all the simple stuff? Quick show of hands, just, okay, right, I'll be as quick as I can then. So you have someone on the laptop here in Bratislava, they want to send a transaction over the Bitcoin network or on Ethereum. They send out a transaction and it goes to the mining pools. So the mining pools collect all the transactions from around the world, they propose a block, and then they give that proposed block to the miners. The miners take the block, they do the proof of work and say, great, here's the block, here's the solution. And then they take that block with the solution, pass it back to the mining pool, and it gets pumped out to the rest of the network. Then there's consensus, magic happens, and it's done. Right. Clear? Good. I've also been told my accent might be a bit hard. So I'm actually from Edinburgh in Scotland, so I appreciate my accent maybe is not the easiest to follow. There isn't much I can do about that, and definitely not tonight, maybe with a couple of beers. But the idea is people want to send transactions, they push it out to mining pools, the mining pools collect transactions from around the world and create block proposals, essentially. They give that to the miners do the proof of work calculation to basically seal the block. And then that gets pushed out to the rest of the network, and then the network comes to consensus and agrees that the block is good. So that's Bitcoin, or Ethereum, or any other chain, essentially. This is basically the exact same thing. Folks, regular people, have transactions, they push it to a mining pool, the mining pool forms a block, goes out to miners, and so on. This again, also blockchain 101, transactions. So that before was like the network perspective, how does the network look across the globe? And here's like the data structure perspective. Each of the transactions at the bottom, they get hashed, go into Merkle root, blah, into a block, and so on. And then how does Polkadot work? So I've almost basically taken the same picture, and where I've got a little C, that is a collator or a collator node, and they replace the mining pools. So they collect all of the transactions in the network, they propose the blocks, and then they push out those blocks to the validators. And the validators are the ones with the little green triangles who are kind of like the miners. They are the ones who do the calculation. It's not proof of work, it's actually proof of stake. So there's no mining involved, and they seal the blocks. They come to consensus and say, yeah, this block is good or it's bad. So this is like the network perspective, and in many ways it's kind of similar. This is the same picture, essentially, giving you an idea of the network in a slightly different way. So the computers are regular people, they want to deploy a smart contract, or they want to send a transaction, and so they've got to push it out to the mining pools, actually the collators, and in this case, I have these circles of different colours. And the circles of different colours are to say that the collators may be slightly different, somehow. And this is coming back to the idea of heterogeneous, or multi-chain. So you can have different types of chains, all connected together. So the top left one might be something like an Ethereum-like chain. The top right could be Zcash or Monero or something else. Maybe it's Cardano or whichever one that you really fancy, for whatever reason. The one the one that you really like. So these collators basically collect up the transactions or the smart contracts for a parachain. So collators and parachains, this idea should be linked in your head. And a parachain is just a blockchain. I'm going to talk a little bit more on that later, but that's what they are. The validators in the middle, again, it's like the miners, they validate all the blocks and say, this is a good block or it's a bad block. So that should be kind of, hopefully that's clear. Is that, show of hands, yeah, nay, roughly. Accent clear? Clear enough, perfect, thank you very much. And this is more, so that was the network perspective, and this is going to be the data structure perspective. The idea again is you have different chains. I'm calling them a para for a parachain. So they have different state machines. They could all be the same or they could all be different. And in the middle, or the kind of pinky purple one, is the relay chain, which is the backbone. And on that chain, we basically have proofs. A proof of that something has happened. A proof that a block is correct. And the idea here is that you have transactions, as I proposed before. They get collected into blocks, but you also want to store the proof of the block to say that this block is valid. So you basically have to have a way of proving that this block is being created in a valid way. And then you want to store that proof somewhere such that people can go back and say, how do I know that this block is valid? And as you can tell, the arrows, basically the arrows are kind of rough. If you really think about the details here, you might think, oh, those arrows look wrong or whatever else. You might have a lot of questions, but don't get too stuck in the details. Just stay with a high level and think, these are, say, transactions or pieces of data that you want to move from one chain to another chain. And this is what we're trying to do. It's kind of Polkadot in one picture. This is taking it slightly further. As you'd guess, I copied and pasted my previous slide, and I've added one at the bottom, which we're going to call Ethereum. So that's outside of Polkadot. It's completely separate from Polkadot. It's got nothing to do with Polkadot. It might not even like Polkadot, who knows. But at the same time, it's still going to be possible to connect Ethereum to Polkadot, or perhaps Ethereum to a single parachain of Polkadot. And so, while Polkadot is this great platform, or at least that's what I want to convince you of, it's not just in isolation by itself. You can get other blockchains which exist right now, and you can connect those into Polkadot. And that's kind of, it's one of the big things that people are excited for. And I don't think I really need to say a bit about, transactions, etc. You can send them across multiple chains. Let me move on. And this is Gavin's wonderful diagram that he presented in London last year. This is quite a magical diagram for me. This was the one that really got me interested in Polkadot. So last year in London, in mid-June, I think, I was sitting in the audience like you are now, and I was like, holy shit, that's some next level stuff. And this was a diagram that really did it for me. I didn't understand the diagram back then, and I vaguely understand it a bit better now, but it's kind of everything that I've said, plus a lot more. And if you can forgive me, I'm going to probably skip on. If you have any questions, I'll be happy to take them later, but I might just move swiftly on. So that's kind of what Polkadot is in a very top level, naive sense, hopefully trying to convince you of the direction that we're going, and hopefully it doesn't sound too crazy. This slide is full of text. I don't think you're going to read it right now. It's not really worth it. If you're watching this on catch up, if you're watching the video, that's great. Then you can pause it and read it. But essentially, these are the problems. And I think there's 7, and I'm going to go through one slide per problem and try to say what they are. So, scalability, Mark 1, storage. So in current blockchains, whether it's Ethereum or Bitcoin, every full node is supposed to store all of the data. That's just what it is. Not every node is necessarily a full node, but every full node should. And you can make some arguments about decentralization is better when there are more full nodes. When each node has more, or there's more copies of the data around. So if only one node had all of the data, then obviously that's a problem. It's debatably not decentralized at that point, or not even debatably, it just isn't. But at the same time, as great as that is, it makes it very, very hard to scale. And what we're seeing is, or not just us, also Ethereum are going to go down the same route. Whenever they do sharding, they're going to say, okay, not all of the data for every single chain will be held by all people. So groups of people will hold data for a particular chain or a particular group of chains, i.e. a subset. So if you're running a full node for a parachain, let's say you're in the bottom right corner, this is, let's just say it's a Zcash parachain, you're holding the data only for that parachain. You're not holding the data for every single parachain. And this is how we're going to get scalability in a horizontal sense. So not necessarily faster, more blocks. This is the idea of scaling outwards. But then at the same time, having blockchains in isolation, obviously I'm trying to convince you that we don't want blockchains in isolation anymore. That's where we are in the world right now. We want to have blockchains talking to each other, but in order to do that, we really just can't have everyone storing everything. It just doesn't scale. And then this is more the vertical scaling, shall we say. The one on the left is something like Ethereum, where it has 15-second block times. I know it's not 15 seconds, it's 12 and a half or whatever it is. Don't worry about that too much. On the right-hand side, we are saying we can have faster block times because of the way that we're designing it, and also because we have multiple chains, then you have multiple transactions in parallel. Not every transaction that you want to do has to go onto the main chain. Whenever Ethereum does sharding, they will also have multiple chains, albeit I think they're going to be homogeneous. So, interoperability. Right now we have blockchains in isolation. That's the left-hand side. And then on the right-hand side, we're saying, okay, let's make all these blockchains talk together. So it's great that you can have a blockchain. That's fantastic technology. That's obviously why we're even here discussing this today. But we have the problem in that it's not so easy to send like a transaction from, say, Zcash to Ethereum. You have to go through, in many cases, a centralized exchange, something like a Binance or a Coinbase or whatever. And we're saying, okay, that's neat, but maybe you can do it in a decentralized way. And yes, there are decentralized exchanges, but we're trying to provide the infrastructure to make it easier to deploy decentralized exchanges. But even that, as interesting as it is not really enough. What we're proposing is actually, how about you want to send arbitrary data from one chain to another chain? How might that look? So not just doing a transaction of like 1 Bitcoin for 1 Monero or whatever, but if you wanted to say have weather data or financial data, something like Bloomberg or Reuters provide all this financial data, and you want to somehow get that on chain, a chain that we'd call an oracle chain. And then if you want to then spread that data around, how do you do that? So if I said, here's all this great data from somewhere like Bloomberg or BBC or Reuters with all this financial data, which is great. If it's on a particular chain, are you locked to that particular chain whenever you build your product? And in the world when there's no interoperability, you're going to be stuck on that one chain wherever the data is, with some caveats. And we're saying, okay, how can we make that easier to share the data across many chains? It isn't necessary that all of the data sits in every chain. They can sit in one chain, but then you want to be able to call that data whenever you need it. So that's kind of part of the idea that we have different chains for different functions, but we don't want to build them in isolation, but we want to build them where they can connect to each other and talk to each other, and then share data amongst each other. Speed, this is a crap diagram, sorry, this is like MS Paint. This is about the best of my skills. The EVM on the left-hand side, if you want to add two numbers together, each number is 256 bits. And you're almost never going to have a number of that size that you want to add together. It just doesn't happen. You don't really need that much address space. So it is a little bit inefficient, shall we say. It was the EVM was designed to work in a way that was easy to price things. And it does that fairly well. But that doesn't have to be the case whenever you're designing a blockchain. You can design it in a different way. And what we're saying is, let's try to remove some of the inefficiencies inside the EVM. We're providing a way to create a chain in a very generic sense where you're not limited just by the EVM's design choices. And partly in doing that, we're finding some of the inefficiencies, removing the inefficiencies such that you can have a faster speed. Some of that will be that you don't have to run, you can run some things at a native speed. So if your client is the latest and most up-to-date, then your client will run at native speed. Currently, if you're using the parity implementation, it's written in Rust, so it'll be as fast as it can go. And then the fallback is WASM. So we have this WASM state machine, which you can basically write the rules for your blockchain. And this is like a worst case, and it's not that slow. It's still a lot faster than the EVM. So this is me trying to convince you that the EVM is maybe not super efficient, not super fast, but we can do better. I guess with WASM things should get improved, but anyhow. And this is one of the, so this is the one which people probably talk about least, or when we say interoperability, people think, yeah, well, it's interoperability, let's have chains talking to each other and let's have decentralized trading, which is great. But if I say to you, what's your idea for a blockchain? Give me your pitch. Create your best blockchain. And then I say, okay, great. How are you going to secure that? Well, I'm going to hassle people in Bratislava to have some miners, and we're going to have the best chain ever in Bratislava. And I say, okay, great. How big is the city here in Bratislava? And you say it's, I don't know, 100,000, 200,000, even 1 million people. How many of them are going to be mining for you? Probably not that many. Okay, then let's look at the rest of the world, and let's try to convince the rest of the world to be a miner on your chain. So this is us on the left-hand side. This is you with traditional isolated security. For every new chain that comes online, you have to essentially pull miners away from the existing pool, or you have to try and find new miners to join. And it's debatably not that easy. There's enough attacks that we've seen on real chains which are not that popular, which have had the 51% attack. It's a problem. And so what we're saying is that we're going to have shared security. So I showed you the relay chain. This is the chain where all the proofs are stored. And we have, I don't want to say centralized, but there's a group of validators who basically do the validation for every block across the entire network. And this is shared validators. So if you spin up a new chain and you connect your chain to Polkadot, there is already a group of validators waiting to validate your chain. So you don't need to find new miners or new validators to join your ecosystem, to join your chain. You might not have that many friends. Not all of us do. So therefore you might not find that many miners, and therefore it might be a problem for this great new idea. And so it'd be great if you could take your innovation and get your blockchain built and deployed without having to worry about something so trivial as finding miners. And that's what we're solving. Next one is privacy. Blockchains are fantastically open and transparent. Some caveats, obviously things like Zcash are not. Monero is not, but things like Ethereum, things like Bitcoin, there isn't really much privacy there. One caveat I will add for Ethereum is that you can have private side chains. Parity have developed a private side chain technology. I believe Enigma are working on something similar. So it exists. This isn't something new, it's not entirely new, but within Polkadot you have the ability to spin up a chain within our platform which is essentially private. You don't necessarily need to share everything which is inside your chain with the rest of the world. So if you have some enterprise application where it could be a consortium of companies who've come together and they want to share data privately amongst themselves, they might not want to share that with the rest of the world, and why should they? But then at the same time, if they are isolated, then they may miss out on all the benefits that the rest of the world has. And it's kind of, how do we give you the benefits of having privacy, where you don't share your secrets, but then at the same time you're able to leverage the opportunities that exist in the rest of the world. And I can't even say it. One more time. Developability. This is one of Gavin's favourite ones. He wants to make it as easy as possible for you to bring your innovation and to get a blockchain up as quickly as possible. If you've seen any of our videos from the Web3 Summit in Berlin, or if you were there, you may remember that Gav did a presentation of spinning up a blockchain on stage. It was quite a magic presentation. You can find it on YouTube. I believe you can also go to our website, web3summit.com, and find the videos. So what did he do? On stage, within the space of an hour, he had someone from the audience come onto stage, open up a new MacBook Pro on stage, so take it out of the box, set it up, download Rust, download the Substrate software. Then he developed modules for this blockchain and then deployed the blockchain live, all within an hour. The actual writing of the chain was probably like 40 minutes into the actual presentation. So he's basically saying, if you want to create your own blockchain, you can now do it a lot faster. And that was kind of the conclusion I wanted to get to. And I couldn't have done that in my previous presentations. When I was in Zurich, and at the end of September, Gav hadn't done his talk. So I've given you the best part, but now I'll come back to the beginning and give you the boring part. So the old days was you had basically, let's just copy Bitcoin, let's create a new blockchain and deploy it. And so people have done that like 20,000 times. And if you're a developer, you might know exactly what's going on, but if you're not, then you might not know what's going on, and how much innovation are you going to be able to bring? How easy is it going to be? Is it fit for purpose? Probably not. And so what Gavin is saying is, let's have a software framework which is modular and highly customizable. So you might want to have pluggable consensus. So you might want proof of work, or you might want proof of stake, or you might want to have different variants, different flavors of proof of stake. And so on the right-hand side, I've called it a Polkadot runtime environment. In Parity, they have this product, shall we say, that they're calling Substrate. So Substrate is a particular type of a Polkadot runtime environment. It's a software development kit. It's basically what you need to build a blockchain in a box. You need, at the bottom, I've got libptp. Libptp is your networking layer. So obviously your nodes within your network have to be able to connect to each other. So everyone in the network has to download the software, but there is a networking layer so they can at least find each other and talk to each other. There's a consensus layer, as you'd expect. It's a blockchain. So you want your network nodes not just to be able to find each other, also to share data, but then also come to consensus. And if you're creating your own blockchain, there's no point in you writing all of this by yourself from scratch. This is like the boring part. You should be spending all of your time closer, rather higher up the stack. And within the Polkadot runtime environment, or with Substrate, we have this WASM interpreter. So it's like a WASM sandbox. And this is where the magic happens for a blockchain. This is where you guys should be doing your development, doing your innovation, and leaving all the boring stuff at the bottom for Parity to do the heavy lifting, the infrastructure stuff. If they do that, then you can do the top part. So in the top part, you have like your accounts and your balances, your smart contracts, your governance, your slashing, your staking, and you want to go down proof of stake. And this is kind of where the innovation is. This is where people will have, it's the state machine or the virtual machine. That's the very top part, that's the runtime. So Cardano, they have a state machine. And it looks a bit different from Tezos, which looks a bit different from Ethereum, which looks a bit different from Bitcoin or Zcash. And that's kind of really where the key differences are in blockchains. Not really in the bottom part, it's mostly generic. And it doesn't make much sense to start again to write that from scratch. This is the bottom part is really what we're paying Parity for. This is the Polkadot runtime environment. And there will be some modules that they will create, of course, for the runtime itself. And this bottom part is written in Rust. So if you know Rust, then you can start going in and you can start tinkering. If you're a developer, you might be willing to learn some Rust. But, as I was saying earlier, we're also keen to pay a team to re-implement this in another language. primarily, or first and foremost, Go. There's a big community who are Go developers in the blockchain space already. We want to get them excited and we want to try and capture those and get them into Polkadot. So if there's Go developers, we would like to speak to them. Oh. Get the good stuff in. And, or C++ or Java. That's more or less the order of preference. So we really hope to get that kicked off as soon as possible. It would be ideal if we could get these alternative implementations before Christmas. Sorry, started before Christmas, and ideally some sort of working proof of concept by end of Q1, so end of March next year. And we are going to pay for this. So the Web3 Foundation, there will be money, a grant available to build this. So it's not just, hope that people can just build it out of the goodness of their hearts. And I think it's really important for decentralization. You don't want to have just one client within your network. If that one client goes down for whatever reason, your entire network goes down. And that's going to be disastrous. And now probably the best one, or the worst, blockchain governance. So on the left-hand side is my great view of current blockchain governance. I went to Google and I searched for Renaissance fighting or Renaissance war or something. And it's kind of how governance feels at the moment. If you want to upgrade a blockchain at the moment, how do you do it? You have to make some proposal somewhere, and hopefully there's a process for doing that. And you need to have enough people to agree with you that your idea is great. And you really need the developers, who are the ones who basically own the repositories where the code sits, that your idea is good. And doing that right now is messy. It's incredibly messy. And we are taking a different view of how the world should be. Not everyone agrees with us, not everyone agrees that we're taking the right direction, but we're making a proposal and we think it should be done in a different way. So the left-hand side is the messy fighting, where you have absurdist trolls on Twitter fighting with each other, saying, oh, you can't have that for whatever reason. And we're saying, okay, no. Let's do this in a different way. If you hold coins or tokens within the Polkadot network, you will have some power to govern how the network is. If you make a bad decision, you may be penalized. You will get hurt. But if you make a good decision, then maybe you do well out of it. But ultimately, it's the people who hold the tokens who get to make the decisions. If you don't hold any tokens, why should you have any power? If I have 0 Ethereum, 0 Ether, but I was really popular on Twitter, if I had like 100 million followers like Katy Perry, and I had a really strong opinion about how Ethereum should be governed, I've got nothing at stake. Should I have any power over Ethereum and how it's governed? I mean, really I shouldn't. But if I have 100 million followers, I could probably do some damage. And it's not a good situation to be in, and we want to avoid that as much as possible. That's not to say that we're perfect or that there isn't problems, but we are trying to make it robust. So the idea is that the coin hodlers, I actually stole this from Gavin, they're the ultimate ones who have the power to decide. So if you hold a token, you can get to decide. You can make a proposal. We think that Polkadot should change like this. That proposal goes on chain. So to make it a bit more concrete, you could have, let's take the relay chain. So the logic of the relay chain, the central part, the state machine, that logic is actually stored on chain. So everyone can see the logic of the state machine on chain. So everyone can say, okay, this is what should be happening. These are the calculations that should be done. And someone might say, okay, but let's update that logic. Let's change that logic. And whenever you update the logic, you make a proposal, and this proposal is public so everyone can see it. And that proposal is also on chain, so everyone can verify what the proposal is, and everyone can vote. There will be some time window for voting upon this proposal. And if the proposal is good and everyone likes it, then this proposal is enforced. Everyone will already have the code downloaded, and if it passes, it will be, say, if there is a yes vote, then in 1,000 blocks, this code will be true. So everyone will already have the code downloaded ahead of the time of it being yes. If there's a no, then obviously nothing happens. But at least in this way, everyone is basically forced to accept the outcome. And part of this is to try and avoid forks, which, okay, we can have some interesting questions there about whether that can actually happen, but this is at least a theory. So you have to have something at stake, you have to be accountable for your actions, and at the same time, you get to be involved, you get to take responsibility. So with great power comes great responsibility. And that is an overview of all the solutions that I just mentioned. Again, it's a text slide, it's kind of boring. I don't really expect you to read it, and if you're watching on a video catch-up, if this is recorded, or if you see one of my recordings online, then you can see a big list of solutions. And now this is the slide where I try to get you all involved with Polkadot. So hopefully I've convinced you that this is worth talking about or worth following. If I haven't, then obviously I've done a very bad job of presenting, and maybe I don't get invited to present again. Hopefully not. He's still smiling, so I think I can come back. So collab.web3.foundation. This is for anyone who is interested either to build or just somehow be involved. So if you want to run a meetup, then you can come here, regardless of what city you're in. You can make us a proposal and say, oh, I really want to host meetups in Vienna or in Bratislava or wherever it is, wherever else you want. We really want to hear from you. If you also want to build a parachain, we want to hear from you. If there's anyone out there in the audience who also wants to build this alternative implementation, if you want to do it in Go or C++, of course then we want to be speaking to you. So if you go to this Collab Web3 Foundation, it's a GitHub repo with all of the open issues. And it's where you can start a conversation. Also, you can reach out to me via email. I'll show that again. And then lastly, what did I say? Yeah, components. So obviously, if you want to have a blockchain, it doesn't make any sense just to have a blockchain by itself. You need to have wallets, you need to have block explorers, and all this good stuff. And we need people to build it. Fortunately, we have people already interested in building a block explorer and building a wallet, but that's not to say that you can't also do it. And that's not to say that we won't pay for this in the future. We have a grants program that we're kicking off formally very soon. If you have an idea right now and you would potentially like funding, then you can already get in touch with me and we can start chatting about what it is you need to submit to get your idea at least reviewed and considered. And the pot of money for grants will be quite chunky. It's not a couple of bucks. It's going to be of the order of thousands of dollars or hundreds of thousands of dollars if it's a rather large project. So the implementation project that we're working on, we expect one implementation probably to be hundreds of thousands of dollars. That's just what it is. If you have to pay 2 or 3 developers full time, going at it, it adds up. The cost adds up. So we have the money to do this, and we are putting our money where our mouth is. We have to do it. That's just how things get built. So I want to get you excited about that. I can't promise you that you will get money, but at least it exists. And if developers don't know that money exists, then they'll never apply. And at least if they do know that it exists, then at least maybe some magic can happen. Learn more, this is pretty standard. Come to polkadot.network. That's where you can start learning about Polkadot. You can find all of our chat channels as well. We use Riot. Wiki.web3 Foundation is actually not just about Polkadot, it mentions Polkadot, but it is our view of a Web3 tech stack. So where do we see blockchains fitting into a general wider picture of Web3? So something like Status, which is a messaging app, that's at the top of the stack, where the users interact, and then you have infrastructure basically down at the bottom, and somewhere in between you have some blockchains, and somewhere in between you have something like IPFS. So this is kind of our view of where we see this decentralized web going, and this is where we see the different teams fitting together. When we did our conference in Berlin, we had the Web3 Summit, and we were fairly agnostic to the teams who came. So it's not just about who are our friends, who likes us, it's more like, what are the good teams working in this space, whether we like them or not, whether they like us or not, let's bring them together and get them to chat to each other. And it's, while maybe it was blockchain heavy, it isn't just about blockchains. So I kind of want to really push that, the idea of Web3 is actually wider than blockchain. And then this is the slide which I knew that everyone would forget. At the beginning, you probably didn't have any questions, you probably didn't care. This time you might, and if there's a chance, even if it's greater than 10%, that you might have a question, then I would say take a note, take a picture, and I'm generally happy to field many questions until you start trolling me or something via email, then maybe I stop. But I'm pretty open. I don't mind. People can send me anything, even collab stuff. We can put it through the repo, or you can come to me directly. You can have a chat. If you are passing through Switzerland, if you're coming to Crypto Valley, to Zug, reach out. I don't mind. If I'm in the office, maybe we can grab some coffee. We can chat about a project. If you're passing through anyway, then you might as well reach out and say hello. And if you're building something even better, then happy to have you come to the office and chat, sit down, have some coffee, and we can talk about your project. If I'm not in the office and you didn't email me, then you might be a bit disappointed. So if you just turn up, knock on our door, expecting someone to welcome you in, they might be looking at you with that kind of WTF look in their face. I think it has happened. Or you're to speak to Ed. He's not here. And they kind of look at you kind of silly. So you're going to be a bit embarrassed. So if you email me far in advance, that would be wise. And we're done. I actually had some bonus slides, but I don't get to present them. So I had to present Alistair's talk last time in Zurich. And I thought I did pretty well. But I'm going to pass you over to the actual expert about consensus and stuff, rather than you listening to me. Oh, we're going to do questions at the end. Yeah.
You can do some now if you want.
We'll do some quick questions now if anyone has them. If you don't, we can take it at the end. Anyone?
Yeah.
Anyone? Was the accent that bad? God damn it.
To be honest, so you can come meanwhile to plug in.
Anyone? Oh, here we go behind you. We have him. Yes.
Maybe one small question. Accent is actually quite okay.
Okay, here comes an essay. Hit me.
But I saw maybe slide 5 or something like that, where you show that one chain is propagating the information to the other chain, and in one is the proof. And what's the proof?
Yes.
That's basically the state of the data, or just the act that nodes agree that this is the representation of the data, or the information then in the various chains be recorded data with the CRC, or you are agnostic of the information and you can do whatever?
It's mostly agnostic as much as possible. It's meant to be essentially as little data as possible. What's the minimum amount of data that you need to prove that the transition from one block to the next was valid? So you have one block, which is like the latest state of your chain. So like in Ethereum, here are the latest transactions. You then want to go to the next block, of which the state changes from block to block. But only a small part of the overall state of Ethereum changes. Only a couple of transactions actually happen within each block. So you only need a small amount of information. And you basically want to have as little information and data as possible. Essentially some cryptographic proof which says that the change from one block to the next was valid. Given everything you know, is that change good? And so if you think of light client proofs, this is kind of the thinking behind it. I don't recall off the top of my head what they are exactly. It's like the Merkle root of the previous block, the Merkle root of this new block, plus a few other things. Basically to prove that the transition was valid, but it is meant to be like as small as it can be. I'm just trying to think if we actually have anything online that you could dig into. Possibly not yet. Like I'm trying to think if there's anything which is really sort of tangible that you could get your hands on that we have online that you could start reading. I have this feeling you kind of get what I'm saying, but without really seeing it written down in front of you, you may not. So, yeah. Unless you can think of a better answer, Alistair. State transition proofs?
Yeah, that's basically it.
Did I say?
About state transition.
Yeah, the state transition proofs. Or what did it look like? What's actually inside?
Well, so yeah, this is what the Polkadot network knows about your parachain. The validators, so collators produce the block, but they're also going to produce basically this proof, this light client proof. And your validators of the relay chain, they're going to switch from parachain to parachain, so they're only really light clients. And what they have is the state transition validation function, which checks, which processes this like client proof that the block is valid. And they sign off on it being valid, so we only include valid blocks. Yeah.
So hopefully we're at least 10% clearer than we were before.
So you are not taking over.
No, go for it.
You are not taking over the job which have to be performed by the blockchain what you are integrating, but you are just consolidating the true into single instance so they can be shared across the blockchains.
Yeah, I think if I understood it correctly. So the really change just takes a proof that some block was correct. The validators have very little data. The validators have as little data as they can get away with. So on a particular parachain, you have all sorts of interesting, cool things happening, like smart contracts or data coming from external sources or a shitload of transactions. And if you imagine doing this really complex stuff 100 times across 100 different chains. So each of these parachains have different sets of data, but somehow they have to talk to each other. And you could imagine some complicated sort of smart contract system sharing data, but that gets really messy. And we're saying there's a centralized chain, if you want to say, which stores a bunch of proofs, which basically is able to prove that a transition from one block to the next is valid. And therefore, if you're trying to send information across the chain, you want to be sure that the information coming to you is valid information, and you want to be sure that ideally that data is finalized. So you don't want to have data come to you like a transaction and then that data to be undone. You don't want like a double spend, for example, or the equivalent of a double spend. So each parachain is responsible for its own data, but in order to talk to another blockchain, another parachain, you have to provide some proof that what you're doing is correct. But you don't have to do it necessarily for every single block. You're just going to have to do it for what's relevant right now. I mean, each block is basically an iteration of history. So the really change is really for the cross, is to make the cross-chain stuff even possible in a simple way.
Okay, thank you very much.
Yeah, no worries.
Maybe we can now go on with us. Maybe one round of applause for Edward.
Hi. Can you hear me?
Yes.
Okay. How about now?
More louder.
So yeah, I'm here to give a talk on consensus for finality. I'll be talking about it'll be some technical stuff, so I'll probably lose half of you. Some things that I've been working on. And what I'm talking about probably it's going to be pretty general. So there's some interesting things in Polkadot consensus about parachains and how this multi-chain system comes together. I'm not going to be talking about that, I'm just going to be talking about one chain. And in particular, how we decide to do things in Polkadot consensus. So, so the question here is about finality. So what's finality? So a block is final when we never revert it. So that's, so who here thinks they understand consensus in Bitcoin? Okay. That's not a lot of you. So the way Bitcoin's proof of work works is in order to produce a new block, you have to solve some puzzle. So for blocks with computing power, there's a random chance you're going to get a hash that's low enough. And then you build on the longest chain. And this magically gives us consensus. So in particular, everyone's going to agree on some increasingly long prefix of what they see as the best chain. How does this work? Well, so the first thing to note is that there will be forks. There will be blocks that aren't on the same chain. But somehow, if the network's good enough and we build on the longest chain, this is going to work. So why is that? So the question is why don't we have long forks in Bitcoin. So what has to happen for us to have, you know, a fork of length 2, of 2 blocks? Well, like, so I suppose this block was first of all these. So why did this guy not build on this block? Well, there's sort of 2 reasons this might be. One of them is that this guy might not have seen this block or processed it when he's solved the proof of work problem. But blocks in Bitcoin are pretty slow, and the network time is that fast. That's unlikely. Another possibility, maybe this block actually appeared sometime later, but this guy is not following the longest chain rule, possibly because he's actively trying to double spend to produce another fork. But if the bad guys don't control much of the computing power, then that's not very likely to happen. So that's how you might end up with this one fork. And now, how do we end up with a fork of length 2 blocks? Well, this has to happen again. So if this guy builds first on this one here, now suddenly this is the longest chain, so we should be building on this one. If this guy comes in second and doesn't build on it, well then either they saw that they didn't see this block, and they thought this block was before this block, whereas this guy thought this block was this block, or they're trying to build the wrong chain. And you can do the analysis about what your assumption of networks are, what your assumption about how many bad guys you've got. And if you do that, you can come up with a bound saying that if this was a few blocks ago, it's probably never going to be reverted. And this basically is probabilistic finality. So, like, what are the properties of this kind of consensus? So one thing it gives you is eventual consensus. Eventually, we'll agree on an increasingly long chain. But all we know for about a particular block is probabilistic finality. And this is annoying, because I don't know if you remember having to wait an hour for 6 confirmations, because whoever it was trying to accept this wanted to have a ridiculously small probability of it ever being reverted. But what it does get you is decentralization. All right, now what do we mean by that? So one thing is that many block producers, anyone with their own CPU, can do this, right? Well, okay, in theory. In practice, they need to be decentralized. Another nice property is this starfish property, right? So some starfish, if you cut them in the right place, you end up with both halves will continue regrowing as a starfish. So if we split the network, then the individual pieces are going to keep on continuing independently. So Ethereum had this concept. Ethereum 2.0 should be able to survive World War III. And something like this is going to help us do that. But another downside of this is that we actually have to be actively listening to the network, actively listening for the longest chain. And a lot of consensus protocols get this kind of property. And not just proof of work, but a lot of proof of stake protocols try and do the same thing. And there's a lot of crazy white papers out there, I'm sure you've all read a few of them, that have many interesting suggestions for consensus protocols. And actually a lot of them have this kind of guarantee. But there's another big school that I want to talk about. And this one starts with this idea called Byzantine agreement. Right. Okay, so in UK English it's like Byzantine, and sometimes I've heard Byzantine, 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 I think I've held all 4 combinations. They call themselves Eastern Roman, but that's why everyone just calls it BFT.
Byzantine.
Yeah. So this classical computer science metaphor, the Eastern Roman generals problem. So we have like a bunch of armies around a city, besieging a city, and they're just trying to decide whether to attack it or not. Each army has its own general, and communication is not instantaneous, right? They don't have radios. And part of the problem is that some of these generals think that they should be the leader and just don't listen to anyone else and do their own thing. And some of them might actually be traitors. Sort of the aim is to design a protocol whereby people can exchange messages and decide whether they should attack or not attack, so that they can all attack the city. If they all attack the city at the same time, they win. If they don't attack, well, they have to decide to attack later. If some of them attack, though, then they'll be defeated and lose. So we have to make sure this is what we're trying to avoid. So we're trying to get an agreement on this attacking on this attack. And we can kind of do the same thing on agreeing on the next block of a blockchain. So this is sort of the kind of thing that Tendermint does very well, and there are many other consensus algorithms that give interesting variants. So like, how does Byzantine agreement on the next block sort of work? Well, it's a bit complicated. I don't have any time to explain this in detail. It's sort of, someone is a leader, but then the leader might not be honest, and we have to sort of rotate leaders, or do something, have random leaders, or do something that means not having leaders. And then we sort of have these votes, and we get these 2 of them, we need to vote, and then we need another vote to say that we saw the result of the last vote. And if that didn't work, we have to repeat it again. And anyway, I don't have time to explain this, but one interesting thing here about how we get fault tolerance against people doing arbitrary things is these votes which need 2/3 of people to pass. So why do we have votes that need 2/3? Well, the idea is that this can help us tolerate up to 1/3 of people behaving arbitrarily. So if we have 1/3 of people up to 1/3 behaving arbitrarily, with a 2/3 vote, the remainder, if they all go for the same thing, it's going to pass. But the reason we don't want a simple majority is because these bad guys could be telling different people that they voted different ways and things like that. And this means that if we went for a simple majority, someone could see a majority for something, someone else could see a majority for something else. But with 2/3, if we went for at least 2/3 this supermajority, then it has to be the case that if we see 2/3 and there are only 1/3 voting for 2 things, then most of the good guys, most of the guys who aren't being taken arbitrarily, must have voted for something for us to get 2/3, and so it's unique. Only one block can be chosen. So what sort of, and the idea is, yeah, we have these guys and they all agree on the next block. And what it gets us, in comparison to the proof of work-like things, what it gets us is fast finality. Everyone, 2/3 of these guys, everyone agrees the block is final, and then we only include finalized blocks on chain. So we don't have to wait for an hour. It also gets us this nice property of asynchronous safety. And what that's about is that it doesn't matter how bad your network is, how long messages take to get from anywhere to anywhere else, and if you have network splits and other complicated things, we never finalize 2 different blocks as long as 2/3 of our guys were honest. But I think one of the most important things is this provable finality. So if 2/3 of people agree on it, what we can get is we can get a statement from these 2/3 of people saying, this is what happened. And what that means is that you don't need to be listening to the network to see that this is fine. You don't need to be listening to the longest chain. And that's great for light clients. It's also very good for other chains. So like Cosmos, to get their communication between chains, they use Tendermint to make all these things final and then pass around these proofs. Polkadot's a bit simpler because we have shared consensus. But like, no, not just that, like the reason why Casper and sharding and Ethereum are coming in at the same time is because they wanted this. It's much easier to communicate between shards if you know this. Okay, but what's a downside? Well, the downside is that everyone has to talk to everyone else. Right, we have multiple rounds of voting in which everyone sends votes to everyone else. And what that means is that either we're centralized, we only have a few guys, 21 or whatever it is in NEOS or whatever, or it's slow to actually produce blocks. Now again, there's lots of consensus algorithms out there that do interesting versions of Byzantine agreement. Like things like Stellar, where you only have to trust your friends. Just like there's many types of things that are like proof of work. These things, they're really wonderful. So the question is can we get some of the guarantees on both sides? Well, okay, the first question is, can we get all the guarantees on both sides? The answer to that is no. So we're only going to include finalized blocks, but we have this, and we're going to be asynchronously safe. So it doesn't matter how bad the network is, we're never going to finalize different blocks. But we also want this starfish property. So if the network splits into two, we want both sides to keep finalizing blocks. But they can't do that because they can't finalize different blocks because of asynchronous safety. And that means they can't produce blocks at all if we have fast finality because we're only adding finalized blocks. So one of these three things, fast finality, asynchronous safety, and the starfish property has to give. And what we kind of go for hybrid consensus is like drop the fast finality. So what I'm talking about here is let's do something. So this is what Ethereum are doing with that Casper FFG. Let's have a consensus algorithm with the properties on the left there, eventual consensus, and let's add a finality gadget, some sort of other protocol on top, which is going to get this this provable finality, get people to sign off on something in a safe way, and it will give us these two things. But the cost of this is that we have to produce blocks and then finalize them later. So we end up with slower finality than block production. And if we want to decentralize this a bit and get more people, it's going to be even slower. But we still have all these things. So we have probabilistic finality before this provable finality kicks in. Because if the if our block production mechanism, if we did proof of work, for instance, and then Casper FFG on top, if that is already agreeing on something, then we're going to vote on top of this and have it agree on the same thing. And so we can already see that this is probably going to work. And we can have lots of people, and we can have this starfish property. But the way that works is that if we separate block production from finality, and we split the network, then we have two sides producing blocks, but maybe neither of them get to finalize. So if we have this situation where, one thing we're particularly scared of is what happens if a third of people go offline. Then we can't get finality in a safe way, it's not possible. but we still keep on going. We still survive World War III, and keep producing blocks. And maybe later we can use we can get this finality started up again. Okay. So I want to say a bit about how Casper works, because we now have sort of an alternative to this. So Casper, we have checkpoints every 50 or 100. It's now 64. Now 128 blocks. We have a vote on this checkpoint. There may be different blocks with this block number, and we vote on them. And if we vote on these, we can finalise a lot of blocks. But we're sort of limited by only 64 blocks together. And we need to get this majority on 2 consecutive checkpoints to finalise everything. And this kind of means we need to measure the time we have to wait for people to vote in terms of the number of blocks. And this is something I wasn't too happy with, because we have no idea how long these things are going to take in Polkadot. So I wanted to come up with some alternative to Casper. And the other sort of motivation in trying to design my own finality gadget was how do we kind of formalise this idea that we start with an eventual consensus. Any one of the crazy block production mechanisms out there, Avalanche or something, which work by network or something, and add finality to it by having a bunch of voters come and do Byzantine agreement. So we decided to come up with our own protocol. So obviously the next question was then, what do you call it? So we had a number of suggestions. Casper AFG, Polkadot finality gadget, family tree, grandpa, ghost case, recursive ancestor deriving prefix agreement, and shaft, shared answering finality tool. Bit of market research, what should we call it? You've answered. Okay, grandpa it is. So, what's the idea behind grandpa? So the first thing is we wanted to have people voting for whatever they thought was the best chain at the time. And particularly one of the differences between Casper is that we don't have these checkpoints. So maybe, some people are going to see this is the best chain, this is the head of this chain, and some people are going to see an extra block. And we kind of want those to both to count for the same thing. And so what we kind of want to do was, so you can sort of consider a vote as a vote for every block before it. I've lost everyone now, right? Yeah, this is all going to be a bit vague. I won't spend too long trying to explain how this works. So sort of the basic idea is that we run one of these Byzantine agreement protocols on every block number in parallel. And sort of the question is, what do we do? And then we can sort of consider one of these 2/3 votes. And the key thing about voting on every block in parallel is what you have to do is we have to agree on some chain. There has to be sort of some consistency. And you've got to sort of design the procedure so that you agree on chains of blocks at once. And the way you do this is you sort of consider, we do one of these 2/3 votes, we have everyone just vote for whatever they think is the best block, whatever they see. And sort of the idea is that if we have probabilistic finality, then it should be that everyone agrees on some prefix already. And we just have to find out what this prefix is. So what we do is we have these votes and we sort of consider each vote as being for all the blocks before it. So we sort of add these things up. And this is what they add up to. And then we sort of consider the 2/3 vote for each of these things in parallel. And like these blocks would have over 2/3, and this chain would be the one that would sort of win this vote. And one of the great things about this is that if we only have a third bad guys, then like any block number, a unique thing's going to have 2/3. And also, if one thing has 2/3, then because all the votes for it and we count for it also count the votes blocked before it, what we're going to happen is we're going to agree on some chain. It's going to be a unique chain. If people see a bit different votes, they might see there's a bit different lengths. Everyone is going to agree on some chain. And the basic idea is we sort of put this into our multiple rounds of voting, and you get something where everyone sort of basically agrees on whatever prefix that 2/3 of people thought was the best chain, including something we agreed on earlier. And hopefully, if you have probabilistic finality, this will mean that we finalise an ever-increasing prefix, which was sort of the aim of trying to get consensus here. So we get something which has the thing we had in Bitcoin, which is we got increasing long prefixes agreed on, but this time we have provable finality. And that's basically the idea of this finality gambling thing, and why we wanted to go with this finality gambling. And that's basically it. Okay, if anyone was following that, do you have any questions?
We could take any general question.
So maybe I can start with the first question. So you mentioned the avalanche consensus mechanisms. What's your take on that? Like, if you maybe compare it.
Oh, it's still so it's an eventual consensus thing, right? It's like one of the definitely definitely needs the network. Yeah, I'm not sure what to say about it. Right? Snowflake was nice. Avalanche is a bit trickier. You have to work out what's a conflicting transaction, and this is why I wanted to work with the block abstraction, right? We have this nice thing with blockchains. Let's work out how many blocks we agree on, as opposed to transactions.
Some other questions?
If you can go back one slide, you have there basically two options. One of them have 40% at the end. Maybe what's the decision criteria? Which one is the best chain? If you have two options where you can add the incremental block down.
Right, so we only agree on the things that we see 2/3 agreement for. So we're not going to do anything with this 40% part. We're going to say we agree on the block that on the chain whose head is this block.
So you will ignore the all incomplete blocks, basically.
We ignore all things that don't have 2/3, might not be unique. Okay. So this is sort of very similar to ghost on votes, except that we don't follow it all the way. We only follow it where we're going to be unique.
So blocks can still be produced, but they don't get finalized. So this is only for the finalization. So like in Bitcoin, you can keep producing blocks. We will keep producing blocks until infinity, but they might not be finalized. So this is like the starfish property. Let's say if the network stopped talking to each other, where half of the world saw one thing and half of the world saw one thing, like the network's cut into World War III, whatever. Both sides, both partitions will keep producing blocks, and they can do that until the end of the world. And what we're seeing here is that you don't get finality, so in Bitcoin there is no finality, it's probabilistic. You think that some transaction that happened 10 days ago is fine, and it kind of is. And for something like Bitcoin, it'd be very hard to revert, but in some other proof of work coins, maybe it would be pretty easy to revert 10 days of work. So your finality is only, it's a chance. It's unlikely that it will be reverted, but it could. And what we're seeing is, or Byzantine finality basically says, let's vote upon this block and say that this block is good and final and can never be reverted. And as long as everyone agrees that that's a good protocol, that block is sealed. If more than 1/3 of people don't agree that that's a good protocol, then you have whatever, you've got shit everywhere. So then forget about it. And what we're seeing here is like you've had the proverbial World War III down the middle here, so there's two partitions, and blocks can keep getting produced. But then at some point, the network may start talking to each other, the partition disappears. And when the partition disappears, you want to be able to have finality, and we can have that. And what we're saying is, okay, at which point did both sides of the partition agree? Because there's very, very likely that they've had the same sort of starting point. They should have started with the same Genesis block, and maybe for 100 years they've all agreed that this is the correct chain. And then World War III happens, or World War IV or 5 or whatever, and you have a split. And then obviously you keep producing blocks, but you can't finalize them because you don't have 2/3 of validators. Your validator set is basically determined long before there's a split. So whenever there's a split, you're always waiting for 2/3 of signatures to come through. But if there's a split, you might not hear from a particular validator or from 1/3 of validators for a long time. And so you don't want the network to be unsafe in that time where you don't hear from a particular validator, because there's been a network split because someone's cut the cable, or there's been World War III, whatever. But eventually, the networks might start talking to each other, the nodes will start talking to each other and sharing data, and eventually you might get these 2/3 of signatures that you need. And you'll eventually be able to see, but there is some shared ancestry. So this is kind of coming back to the shaft, that it's shared ancestry between blocks, or between entire chains. So you could have like 1 million blocks here, and then the bottom one could be another 1 million blocks. But you'll find that actually there was some shared history back in the past where they can agree upon and say, okay, we can agree upon that. And moreover, we can say one of the two chains is actually preferential over the other because of the number of signatures, basically.
Okay, so yeah, the important thing here was that we agree, we're going to finalise anything we see 2/3 for. If we go beyond the end of that, to this thing where we have 40%, we don't have 2/3, so we're going to finalise that later. Mm-hmm. Once we agree on the things that everyone already agrees on.
There's a pretty good blog on Medium, or two. So medium.com/Polkadot-network. And we have a bunch of blogs about Polkadot. One of them that I wrote, which is about consensus from Bitcoin to Polkadot, which is basically Alistair's presentation, similar, it's kind of covering the history. So that's a good place to start to get from kind of like the basics, the fundamentals, and then get through to where we are. And then Rob Habermeyer, who is a dev at Parity, who's working on Polkadot, he wrote all about Grandpa, which is what we're calling this. And that's kind of covers some things that I cover in my blog, in my history piece, and then goes a bit further. And then if you really want to get hardcore, you can read Alistair's PDF, which has all the gory details. So it kind of depends on your appetite.
Yeah, of course.
So when it comes to splitting those two chains, and there will be unclosed blocks, that would be caused by some event that was fraudulent and happened to network to not being able to make the consensus to close them.
Why would we get a network split? Well, obviously there's World War III. And so one of the things that's happened in practice in the past has been that someone has released some version of some client with a bug that means different clients behave differently, and that would cause a network split until the bug was resolved.
So it's accidental.
Okay, but anyway,
the other reason is deliberate. There's people disagree.
accidental.
But let's say those changes will be producing blocks by their own, and what will happen to the changes on the original chains that were made during the producing empty blocks, basically before they agreed on the right chain?
So yeah, if we have a network split and both sides keep producing blocks, then we don't finalise anything because we can't get 2/3 votes. If later they come back together someone connects these two sites together.
Oh, and then
Then we'll say
Oh, okay.
one of these chains will be longer, or whatever our agreement was will be better. And, yeah, very
So those changes will be transferred to the.
and then we'll agree on one of these chains, and it won't have the transactions on the other. They might not make sense. Yeah, and the transactions that still make sense might come in. But yes, if we have a long fork, we're just going to forget about one. The important thing about finality is we're going to agree eventually that this is going to be solved. It's bad. We don't want that happen.
You were talking about the finality, how you achieve it with 2/3 of signatures. So I was wondering, how do you prevent the nothing at stake problem, or does it affect it? I mean, can it happen that you actually get 2/3 for one chain, and then later on you will get maybe the same validators signing for another fork?
Right. We can have slashing.
You have some slashing conditions.
Yeah. And if it's on the same block, right, on the same voting round, if you vote for different chains, that's easy. We catch that. We slash it.
If it's not, if it's
well, then it's a bit tricky. So what we have is we have a kind of challenge procedure where we sort of say that, well, why did you vote this way? So we have this asynchronously safe protocol that says that, like, if only 1/3 of people are Byzantine, then if you vote this way, it's going to be safe. So what we do is you ask the guy, why did you vote this way? What were these votes you saw in the previous round that made you think this was safe? And then they'll come up with some votes on the previous round, of which at least over a third, are going to contradict this thing that was finalised earlier.
So there's some
And
kind
then
of
you sort of repeat that until you find some equivocations or someone who just voted this way unsafely for no good reason. And you're going to find over a third of people, and you're going to slash them. So one of the issues
work actually.
one of the issues with that is what happens if most people are wrong and you do it on the same chain, and maybe you have to, hard fork the entire thing and then go through this process on another fork and work out who to blame. But there is a process to find the people that did something wrong.
You also have this written somewhere, like a paper or something about, yeah?
Yes, I have a write-up of most of this. Not quite how to do. So I've got this challenge procedure, but I don't know quite how to do it. But that's how you prove safety. You say that if it's not safe, we can find these guys. Yeah, I have a write-up. If you look for, if you Google, W3F consensus, GitHub, go to the GitHub W3F consensus PDF, the grandpa.pdf, which will have all the gory details. It doesn't entirely make sense yet. I'm still trying to write a paper on this. Eventually, it will be peer-reviewed and everything.
Is it also safe against some long-range attacks? Like if the validator loses his keys or sells them on the market later on, like let's say after he doesn't need them anymore, or he's not concerned about the blockchain anymore. Have you also thought about that?
One of the great advantages of this kind of let's finalize everything is that it's far less vulnerable to long-range attacks. With longest chain and these kind of proof-of-stake things, that's a problem. But it's not a problem for this. But there is a danger, you can long-range attack light clients who are not paying attention to the network by having some agreement a long time ago. But everyone else should have already finalised this. And they're never going to revert.
You are new on the network, like joining with a fresh node, and basically you have no way of like were you perhaps thinking about doing some centralized checkpointing, or
That's basically how it has to happen here.
The relay chain. That's right.
Right, this is all. Yeah. Basically, that's how it has to happen. There has to be a centralized checkpointing. You have to say that you all agree that this happened. And if you're running something else, you're not running Polkadot.
Centralization in a logical sense. It's a decentralized network, just in case people get religious on us. It can happen in this case, right?
okay, thanks.
Some other questions? Someone? Okay, I think in that case, thank you guys very much for your talks. Yeah, like we can move to the informal part now with the snacks and stuff. Maybe a beer later. Cool. So thank you everyone for coming, and see you on the next meetup on 5th of December.